Picture an iceberg floating in the endless ocean. What you see above the water is just the tiniest fraction of its true size. Now imagine the universe is exactly like that. The stars, the galaxies, the planets, everything we can observe with our most powerful telescopes makes up a mere 5% of all that exists. The rest, a vast, invisible ocean of dark matter and dark energy, two of the most baffling mysteries in modern science. These hidden forces shape the very fabric of the cosmos, pulling and pushing the universe in ways we're only beginning to understand. And yet, despite decades of research, they remain elusive, dancing just beyond the edges of our comprehension. What if I told you that the universe as we know it is just the tip of an unimaginably vast cosmic iceberg? That the night sky, filled with its glittering stars, is only a fraction of the real story? Dark matter, an invisible scaffold holding galaxies together, and dark energy, the mysterious force accelerating the expansion of the universe, make up the other 95%. Think about that for a second. Everything you've ever seen, touched, or known is dwarfed by something we can't even detect directly. It's like living in a house where the walls, the floor, even the air are made of something completely unknown. Scientists have been chasing these shadows for decades, and what they've uncovered will absolutely blow your mind. That's why today we're diving deep into the cosmic unknown to unravel 25 mind-blowing facts about dark matter and dark energy. From ghostly particles that pass through you every second to the terrifying possibility that dark energy might one day tear the universe apart, we're going to explore the cutting-edge discoveries that are rewriting our understanding of reality. This isn't just science, it's the greatest detective story of all time, and you're about to become part of it. So buckle up, because by the end of this journey, the universe is going to look very, very different. Ready to uncover the secrets hidden in the dark? Let's begin. Here's something that will bend your brain. Dark matter is everywhere, yet we can't see it, touch it, or even detect it directly. Imagine a cosmic puppet master pulling the strings of the universe, completely invisible but undeniably powerful. That's dark matter for you. Scientists estimate it makes up roughly 27% of the cosmos, nearly 6 times more than all the ordinary matter, stars, planets, you and me combined. And here's the wild part, it doesn't interact with light at all. No glow, no shadow, no reflection. If you shone the brightest flashlight in the universe at it, you'd see nothing. So how do we even know it exists? Because of its gravitational grip. Take galaxies, for example. They spin so fast that, according to the laws of physics, they should fling themselves apart. But they don't. Something unseen, dark matter, acts like an invisible scaffold, holding them together with its gravitational pull. It's the reason galaxies cluster like beads on a string across the universe, shaping the largest structures we can observe. Without dark matter's hidden hand, the cosmos as we know it wouldn't exist, and the weirdness doesn't stop there. Dark matter doesn't just sit still, it moves, flows, and even creates a cosmic web that channels the formation of galaxies. Picture pouring syrup onto a plate and watching it spread into thin, interconnected strands. That's how dark matter sculpts the universe, guiding where stars and galaxies will form. Yet, despite all we've pieced together, we still don't know what it's made of. Is it an undiscovered particle, a cosmic ghost from the dawn of time? Every experiment so far has come up empty, leaving scientists chasing shadows in the dark. One thing's for sure, without this mysterious, invisible glue, the night sky would look very different, maybe even empty. So the next time you gaze up at the stars, remember, what you're seeing is only the smallest part of the story. The rest is hiding in plain sight, shaping everything from the tiniest galaxy to the grandest cosmic web, and we're just beginning to uncover its secrets. While dark matter holds the universe together, dark energy is doing something far more unsettling. It's ripping it apart. Picture blowing up a balloon with tiny dots on its surface. As the balloon expands, the dots move away from each other. Now imagine someone suddenly pumping air into that balloon faster and faster. That's exactly what dark energy is doing to our universe, an invisible force accelerating the expansion of space itself. This mind-bending discovery came in 1998 when two teams of astronomers made an observation that would win them the Nobel Prize. By studying distant supernova, the explosive deaths of massive stars, they expected to see the universe's expansion slowing down due to gravity's pull. Instead, they found the opposite. These cosmic explosions appeared dimmer than they should have, meaning they were farther away than predicted. The shocking conclusion. The space between galaxies wasn't just expanding, it was accelerating. Here's where things get cosmic-level strange. Dark energy makes up a staggering 68% of the universe's total content, more than twice as much as dark matter. Unlike matter that clumps together, dark energy appears perfectly smooth, stretching space uniformly in all directions. And the more space expands, the more dark energy there seems to be, creating a runaway effect that could eventually leave galaxies isolated in vast, ever-growing voids. What could possibly be causing this? The leading theory points to something called vacuum energy, a property of empty space itself that causes repulsion rather than attraction. Think of space as being filled with an invisible spring, constantly pushing outward. The craziest part, we don't know if this acceleration will continue forever, rip atoms apart in a big rip scenario, or even reverse someday. One thing is certain: dark energy has rewritten cosmic history. Without it, we'd live in a very different universe, one where gravity would eventually pull everything back together in a big crunch. Instead, we're riding an expanding wave of space-time, carried by a mysterious force we've only begun to glimpse. The same discovery that answered one fundamental question, how will the universe end, opened countless others about the true nature of reality. If you could see dark matter with the naked eye, the universe would look nothing like the scattered stars we recognize instead. You'd witness an intricate, glowing spiderweb stretching across billions of light years. This is the cosmic web, the hidden architecture of the cosmos, woven from threads of dark matter so massive they bend space itself. Picture dew clinging to a spider's silk on a misty morning. Those droplets are like galaxies, strung along these invisible filaments with vast, empty voids stretching between them. This web didn't form randomly. In the moments after the Big Bang, tiny ripples in the fabric of space-time gave dark matter something to cling to, and over billions of years, gravity sculpted these ripples into a sprawling, interconnected network. The scale of this structure is almost impossible to comprehend. A single filament can stretch for hundreds of millions of light years, linking clusters of galaxies like beads on a string. And just like a spiderweb trembles when disturbed, the cosmic web vibrates with the motion of galaxies sliding along its strands, pulled by the irresistible tug of dark matter's gravity. Without this scaffold, galaxies would be adrift in a featureless sea of darkness. Instead, they're drawn together at the intersections of these filaments, piling up into dazzling superclusters, some of the largest structures in the known universe. But here's what's truly mind-bending. We're not just observers of this web, we're part of it. Our Milky Way sits on the fringes of a filament called the Laniakea supercluster, a river of galaxies hundreds of millions of light years long, all flowing toward a mysterious gravitational focal point astronomers call the Great Attractor. Yet even this colossal structure is just one thread in a tapestry far grander than we can fully map. The cosmic web doesn't just guide galaxies, it shapes their fate. Galaxies born along dense filaments grow faster and larger, feasting on the steady stream of gas channeled by dark matter. Meanwhile, those stranded in the voids between threads are starved of material, left to fade into isolation. It's a cosmic feeding frenzy, with dark matter as the silent puppeteer. And the most haunting question of all, we're still only seeing shadows of this web. Advanced simulations reveal its structure in stunning detail, but mapping it in reality is like tracing the outline of a city using only the glow of streetlights. Most of the metropolis remains hidden. Every new observation peels back another layer, showing us just how much of the universe's true form has been hiding in the dark all along. Here's where things get really interesting. Dark matter and antimatter sound like they could be cosmic cousins, but they're actually as different as night and day. Antimatter is like matter's evil twin. Every particle we know, from electrons to protons, has an antimatter counterpart with opposite properties. When matter and antimatter meet, they annihilate each other in a burst of pure energy, a phenomenon we've actually observed in labs. Scientists can create and study antimatter, trapping it in magnetic fields to examine its behavior. It's rare in the universe, but it's undeniably real, leaving behind traces we can detect. Dark matter, on the other hand, plays by entirely different rules. It doesn't annihilate with regular matter. It barely interacts with it at all. While antimatter produces dazzling bursts of energy when it collides with matter, dark matter passes through everything like a ghost. Imagine standing in a room where countless invisible particles are streaming through your body every second, leaving no trace. That's dark matter, utterly indifferent to the world of atoms, yet shaping the universe on a colossal scale through gravity alone. Why does this distinction matter? Because antimatter follows the well-trodden paths of particle physics, obeying the rules we've painstakingly mapped out over the last century. Dark matter defies them. If antimatter is the rebellious sibling we can reason with, dark matter is the enigmatic stranger who refuses to speak our language. And here's the kicker: antimatter makes up just a tiny fraction of the universe, while dark matter outweighs all visible matter by a factor of 5. This isn't just academic curiosity, it's a clue to one of physics' greatest puzzles. The fact that dark matter doesn't behave like antimatter or any known particle suggests there's an entire shadow universe of physics waiting to be discovered. Maybe dark matter is part of a hidden sector of particles that barely interact with ours, or perhaps it's a sign that gravity itself works differently on cosmic scales. Every experiment hunting for dark matter particles has come up empty, forcing us to rethink our assumptions about how the universe is built. So next time someone mixes up dark matter and antimatter, remember, one is a fleeting cosmic spark we can capture and study, while the other is the silent architect of the cosmos, weaving galaxies together in ways we're still struggling to comprehend. And that mystery is what makes dark matter one of the most tantalizing puzzles in all of science. One of the most spectacular pieces of evidence for dark matter came from a violent cosmic collision nearly 4 billion light-years away, the Bullet Cluster. Picture two galaxies smashing into each other at millions of miles per hour, a cosmic car crash unfolding over hundreds of millions of years. The visible matter stars, gas, and dust clashed so fiercely that the galaxy's gas clouds heated up and slowed down like two clouds of smoke merging and swirling. But something bizarre happened with the gravity. When astronomers mapped the cluster's mass using gravitational lensing, the way massive objects bend light from distant galaxies behind them, they found the bulk of the gravity wasn't where the visible matter was. It was offset, as if the true mass had ghosted right through the collision. This was the smoking gun for dark matter. Unlike normal matter, which interacts and slows down during collisions, dark matter passed through unscathed, carrying its gravitational influence with it. Think of it like two crowds of people running into each other in a dark field. The people ordinary matter collide, bump, and slow down, but invisible marathoners, dark matter, keeps sprinting straight through without stopping. The Bullet Cluster showed this separation in stunning detail. The hot gas from the galaxies, detected by X-ray telescopes, lagged behind while the gravitational lensing revealed most of the mass had surged ahead. Here's why this was such a breakthrough. It ruled out alternative theories that tried to explain galactic motions by tweaking gravity itself. If gravity behaved differently on large scales, the lensing effect would have stayed aligned with the visible matter. Instead, the clear disconnect between the visible gas and the gravitational footprint screamed one thing: dark matter is real, and it's something entirely separate from the atoms we know. The bullet cluster didn't just confirm dark matter's existence, it revealed how it behaves. Dark matter doesn't crash, compress, or emit light when it interacts. It's frictionless, silent, and dominant, shaping the universe while remaining utterly indifferent to the visible drama unfolding around it. And because of that, we now know galaxies aren't just held together by what we see. They're anchored by vast, invisible halos of this mysterious substance, drifting through the cosmos like shadows. Gravity has always been the universe's great sculptor, pulling matter together to form stars, galaxies, and even clusters of galaxies, but dark energy. It's the cosmic rebel, defying gravity's pull with a repulsive force so powerful it's stretching the fabric of space itself. Imagine blowing up a balloon while someone keeps tightening rubber bands around it. Gravity tries to squeeze the universe back together, while dark energy keeps inflating it faster and faster. This isn't just a gentle nudge, it's an accelerating push that's fundamentally changing the fate of everything. Scientists call this repulsive force negative pressure, a bizarre property of empty space that sounds like science fiction but is very real. Here's how it works. As the universe expands, more space appears, and with it comes more dark energy. It's like a cosmic feedback loop. The bigger the universe gets, the stronger dark energy becomes, driving expansion to ever-increasing speeds. Unlike gravity, which weakens with distance, dark energy's influence grows as galaxies move farther apart, making it the ultimate long-range force in the cosmos. The implications are staggering. Billions of years from now, distant galaxies will be racing away so fast their light will never reach us again. The universe won't just be expanding, it'll be accelerating into isolation, with galaxies vanishing over the horizon like ships lost in a thickening fog. And the weirdest part, dark energy isn't some exotic substance filling space, it's a property of space itself. Think of it like a hidden tension in the vacuum. An infinite energy woven into nothingness that's stronger than anything else in existence. But why does space have this repulsive quality? One leading idea points to quantum physics, where particles constantly flicker in and out of existence, creating a seething energy in what we call empty space. Normally, these fluctuations cancel each other out, but on cosmic scales, they might add up to the relentless push we call dark energy. There's just one problem. When physicists calculate how much energy this quantum foam should contain, the numbers are off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It's the biggest mismatch between theory and observation in all of science, hinting that we're missing something profound about how reality works. Some theories suggest dark energy might not even be constant. It could change over time, growing stronger or weaker in ways that could rewrite the universe's destiny. Will it eventually tear apart galaxies, then stars, then even atoms in a catastrophic big rip? Or could it fade away, allowing gravity to regain control? Right now, we're left watching the cosmos expand at an ever-quickening pace, driven by a force we can't see or touch but whose influence is everywhere. It's as if the universe has a hidden engine and we're just beginning to hear it roar. If dark matter is out there, what exactly is it made of? Scientists have two leading suspects: ghostly particles that could be hiding in plain sight, just waiting to be discovered. The first candidate, WIMP, short for weakly interacting massive particles, are exactly what they sound like: hefty, sluggish particles that barely acknowledge ordinary matter exists. Picture a crowd of people packed into a stadium, unaware of the invisible giants casually strolling through them, never bumping into anyone. That's how WIMP would move through the universe, unchallenged, undetected, yet massive enough to bend space with their gravity. The hunt for WIMP has driven some of the most ambitious experiments in physics. Deep underground, shielded from cosmic noise, detectors filled with ultra-pure liquids or crystals wait for the once-in, a lifetime moment a WIMP might collide with an atom, releasing a faint flash of light or vibration. Meanwhile, the Large Hadron Collider smashes protons together at nearly the speed of light, hoping to briefly conjure these elusive particles into existence. So far, no luck, but the search has only grown more creative, pushing detectors to impossible sensitivity and rewriting theories about where WIMP might hide. Then there's the second candidate, axions. If WIMP are the heavyweight contenders, axions are the featherweight phantoms, hypothetical particles so lightweight they could slip through detectors like whispers through a wall. But here's the twist, axions might not be entirely dark. In strong magnetic fields, theory suggests they could transform into photons, leaving behind a faint, telltale glow. Experiments like ATMs are essentially giant radio receivers tuned to the universe's quietest station, listening for the murmur of axions converting into detectable waves. The stakes couldn't be higher. Discovering WIMP or axions wouldn't just solve the dark matter puzzle, it could crack open entirely new branches of physics, revealing a hidden layer of reality. Or perhaps neither particle exists and the answer lies somewhere even stranger. Every null result, every silent detector, forces us to rethink the boundaries of what's possible. One thing's certain, the hunt for these cosmic ghosts is far from over, and the moment we find them, the universe will suddenly make a lot more sense or a lot less. The universe might seem eternal, but dark energy has locked it onto one of several terrifyingly possible endings, each more dramatic than the last, the most likely scenario. The Big Freeze. Imagine a cosmic winter where galaxies drift so far apart that the night sky goes utterly black. Stars burn out, black holes evaporate, and the universe settles into an icy, silent equilibrium, a state of maximum entropy where even time loses meaning. With dark energy accelerating expansion, galaxies beyond our local group will eventually vanish over the cosmic horizon, their light stretched into undetectable infrared whispers. The universe won't end with a bang, but with the slow fade of an ember dissolving into endless, empty space. But what if dark energy isn't just constant? What if it grows stronger over time? That's where the Big Rip comes in, a nightmare scenario where the repulsive force of dark energy overwhelms everything. First, galaxy clusters would be ripped apart, then individual galaxies. Stars would detach from their orbits, planets would disintegrate, and eventually, even atoms would be torn asunder, unable to withstand the space-time stretching around them. Picture a loaf of raisin bread baking in an oven that never stops expanding. The raisin's galaxies stay intact at first, but as the dough space stretches faster and faster, even the raisins themselves are pulled apart. This could happen in as little as 22 billion years, a blink on cosmic timescales. Yet there's a third, stranger possibility. Dark energy might not be constant at all. Some theories suggest it could decay or flip into an attractive force, reversing the expansion. The universe could collapse in a big crunch, a mirror of the Big Bang where everything, space, time, matter, implodes into a singularity. Or perhaps dark energy will oscillate, driving cycles of expansion and contraction in an endless cosmic heartbeat. Here's the chilling truth. We don't know which path the universe will take because we still don't understand dark energy's true nature. Is it Einstein's cosmological constant, a fixed property of the vacuum, or something dynamic evolving alongside the cosmos? Every observation of distant supernova, every map of galaxy clustering brings us closer to the answer. But until then, we're left with a universe balanced on the edge of possibilities, its fate written in shadows we're just beginning to trace. One thing's certain, dark energy isn't just shaping the universe, it's holding the pen that writes its final chapter. Without dark matter, the night sky would be an empty void, no glittering stars, no swirling galaxies, just endless darkness. That's because dark matter did something extraordinary in the early universe. It built the scaffolding for everything we see today. Picture the cosmos just after the Big Bang, a searing hot soup of particles and radiation. Ordinary matter, the stuff that makes up planets and people, was too chaotic to clump together, constantly buffeted by intense heat and pressure. But dark matter, unaffected by light or radiation, began to collapse under its own gravity, forming vast, invisible clouds. These weren't just random patches. They were the universe's first blueprints, gravitational traps that captured ordinary matter and sculpted it into galaxies. Here's how it worked. Dark matter's gravity created wells in the fabric of space-time, like dimples on a rubber sheet. Gas and dust, drawn by these invisible pits, pooled at the center, growing denser and hotter until nuclear fusion ignited, the birth of the first stars. Without dark matter's pull, this gas would have remained scattered like smoke drifting in the wind. But with its help, stars clustered into galaxies, galaxies gathered into clusters, and the cosmic web emerged, stitching the universe together. Now imagine the alternative, a universe without dark matter. Gravity from visible matter alone would have been too weak to overcome the expansion of space. Stars might have formed sporadically, but they'd be isolated, adrift in a vast emptiness. No Milky Way, no Andromeda, just a lonely sea of flickering lights too far apart to ever collide or merge. The universe would lack structure, a featureless expanse where life as we know it could never take root. What's even more astonishing is how precise dark matter's role was. Too much and galaxies would have collapsed into supermassive black holes. Too little and nothing would have formed at all. It's as if the cosmos had a perfect recipe, a pinch of visible matter, a heaping scoop of dark matter, and stirred them together at just the right moment. Even now, dark matter continues shaping galaxies, determining whether they'll grow massive or remain small, spiral or elliptical. So when you look up at the stars, remember, you're seeing the aftermath of a cosmic partnership where the invisible sculpted the visible into existence. Dark matter isn't just some mysterious add-on to the universe, it's the reason the universe looks the way it does at all. Einstein once called it his greatest blunder, but it turns out he might have been more right than he ever imagined. Back in 1917, while working on his theory of general relativity, Einstein introduced a fudge factor called the cosmological constant. At the time, scientists believed the universe was static, neither expanding nor contracting, so Einstein tweaked his equations to include this mysterious repulsive force, balancing gravity's pull to keep the cosmos perfectly still. But when Edwin Hubble discovered the universe was actually expanding in 1929, Einstein dismissed his own idea as unnecessary, brushing it aside as a theoretical misstep. Decades later, the joke's on us. When astronomers found the universe's expansion wasn't just continuing but accelerating, they realized something eerily familiar was at work, a repulsive force acting against gravity on cosmic scales. Sound familiar? The cosmological constant had come roaring back, this time as the leading explanation for dark energy. Einstein's blunder wasn't a mistake, it was a stroke of intuition decades ahead of its time. What makes this twist even richer is that Einstein didn't just abandon the idea, he actively rejected it. Yet buried in his equations was the key to one of the biggest discoveries in modern cosmology. Today, physicists debate whether the cosmological constant truly represents dark energy or if it's something more complex, but either way, it's a humbling lesson in scientific humility. Even geniuses doubt themselves, and sometimes the answers hide in plain sight, waiting for the right moment to be rediscovered. The irony: if Einstein had trusted his original instinct, we might have unraveled dark energy's mystery much sooner. Instead, his self-doubt left the puzzle unsolved for generations, a reminder that in science, even the wrong ideas can contain seeds of truth if we're willing to revisit them with fresh eyes. When we think of dark matter, it's tempting to imagine it's made of something familiar: rogue planets drifting between stars, black holes lurking unseen, or even vast clouds of cold gas. After all, the universe is full of ordinary matter that doesn't glow, So why couldn't that explain the missing mass? This stuff, known as baryonic matter, the protons, neutrons, and electrons that make up everything from your coffee cup to distant quasars, does hide in plain sight. But here's the catch: there's just not enough of it to account for the gravitational effects we observe. Take rogue planets, for example. These are worlds untethered to any star, wandering the galaxy like cosmic nomads. While they don't emit light, they do block or bend background starlight when passing in front of it, a phenomenon called microlensing. Astronomers have searched for these dark giants, but even the most generous estimates suggest they contribute less than 1% of the dark matter needed. The same goes for black holes. Primordial black holes, hypothetical leftovers from the Big Bang, were once a promising candidate, but detailed surveys like the ones monitoring the flickering of distant stars haven't found nearly enough of them to fill the gap. Then there's the gas problem. Clouds of cold hydrogen, the building blocks of stars, are invisible to optical telescopes, but they emit faint radio waves, and when astronomers tuned in, they found only a fraction of the missing matter. Even the hottest gas, glowing in X-rays between galaxy clusters, adds up to just a drop in the cosmic bucket. The verdict: baryonic matter can't be the hero of this story. At best, it's a minor character in a much weirder plot. So what's left? The overwhelming majority of dark matter must be something exotic, a substance that doesn't just hide from light but fundamentally ignores it. Unlike baryonic matter, which interacts via electromagnetism, giving us light, chemistry, and even life, dark matter seems to play by different rules. It's as if the universe has two parallel sets of physics, one for the world we see and another for the shadow realm that shapes it. That's why scientists are chasing particles unlike anything we've ever detected. WIMP actions or even undiscovered forces could hold the key. The deeper we dig, the clearer it becomes. Dark matter isn't just ordinary matter in disguise. It's a cosmic stranger rewriting the rules of reality as we search for its fingerprints. Vera Rubin stared at the data in disbelief. The numbers didn't lie. Stars at the outskirts of galaxies were moving so fast that by all known laws of physics, they should have been flung into the void. Yet there they were, orbiting as if held by an invisible hand. This was the puzzle that would redefine our understanding of the cosmos. In the 1970s, Rubin and her colleague Kent Ford meticulously tracked the rotation of the Andromeda galaxy, measuring the velocity of stars at different distances from its center. What they expected to see was an orderly drop-off in speed, just like planets in our solar system, where Mercury zips around the Sun far faster than distant Neptune. Gravity weakens with distance, so outer objects naturally move slower. But galaxies played by different rules. Instead of slowing down, stars at the edge of Andromeda were whizzing around at nearly the same speed as those near the core. It was as if a car speeding down a highway could maintain 90 miles an hour without pressing the gas pedal, an impossibility unless some unseen force was at work. Rubin realized the only explanation was a massive halo of invisible matter surrounding the galaxy, its gravity gripping the stars tight enough to prevent them from flying away. These galactic rotation curves became the smoking gun for dark matter, proving that what we see isn't just a fraction of what's out there, it's dwarfed by what we can't see. The implications were staggering. If visible matter were all that existed, galaxies would have torn themselves apart billions of years ago. Instead, dark matter's gravitational scaffolding holds them together, its influence stretching far beyond the luminous disk of stars we observe. Picture a merry-go-round spinning so fast that the riders should be flung off except someone nailed down their shoes. Dark matter is that unseen anchor, keeping everything stable against forces that should spell cosmic chaos. Rubin's work didn't just solve a mystery, it shattered assumptions. Before her findings, many scientists clung to the idea that the universe was made of familiar stuff, with any anomalies due to measurement errors or incomplete data. But rotation curves don't lie. Study after study confirmed the same bizarre pattern in galaxy after galaxy. forcing astronomy to confront an uncomfortable truth. Most of the universe's matter doesn't interact with light at all. It doesn't glow, absorb, or reflect. It simply is, exerting its pull in silence. What makes Rubin's discovery even more remarkable is how elegantly it complements other dark matter evidence. From gravitational lensing to the cosmic microwave background, every independent line of inquiry points to the same conclusion. The stars at galaxy edges aren't moving too fast. We've been underestimating the mass holding them in place all along. And while Rubin herself shied away from the spotlight, her legacy is written across the night sky, in every spinning galaxy that defies expectation, whispering the same undeniable truth. The universe is far stranger and far darker than we ever imagined. Here's something that defies common sense. Dark energy doesn't thin out as the universe expands. Picture blowing up a balloon with a few dots drawn on it. As the balloon inflates, the dots spread apart, becoming more scattered. This is how ordinary matter behaves in the cosmos. The farther apart galaxies drift, the more diluted their mass becomes, weakening gravity's pull over vast distances. But dark energy, it's the ultimate rule breaker. No matter how much space stretches, dark energy's density stays exactly the same, as if the universe's expansion is magically creating more of it to fill the void. This bizarre property is what makes dark energy the ultimate cosmic powerhouse over time. In the early universe, matter, both dark and visible, dominated the cosmic tug-of-war, its gravity slowing the expansion. But as space grew, matter's influence faded, spread thin across ever larger volumes. Dark energy, unwavering, gained the upper hand. Imagine a marathon runner who never tires no matter how far they go. Their speed stays constant while everyone else falls behind. Billions of years from now, the last galaxies beyond our local group will vanish over the horizon, their light stretched beyond detection, all because dark energy's relentless push never weakens. The implications are staggering. Unlike matter, which clumps into galaxies and clusters, dark energy is perfectly smooth, stretching space uniformly in all directions. It's not tied to any particle or field we know. It behaves like a property of empty space itself. Think of it as an infinite, invisible spring threaded through the cosmos, always pushing outward with the same tension, no matter how much it's stretched. Every cubic centimeter of vacuum, whether in the void between galaxies or the empty space inside atoms, hums with this same repulsive energy. Why does this matter? Because it flips our intuition about how the universe evolves. In a matter-dominated cosmos, gravity would eventually pull everything back together in a big crunch. But dark energy's constant density ensures the opposite. An accelerating expansion where galaxies are torn apart not by force, but by the relentless creation of space between them. It's like two people trying to walk toward each other on a moving sidewalk that keeps speeding up. No matter how hard they try, the distance only grows. The craziest part, we still don't know why dark energy's density stays constant. Quantum physics predicts vacuum energy should exist, but the calculated value is off by a factor of 1 followed by 120 zeros, the worst prediction in all of science. This cosmological constant problem hints that we're missing something profound, perhaps a hidden symmetry or an entirely new framework for spacetime itself. One thing's certain, dark energy's unchanging nature is rewriting cosmic history. It didn't just nudge the universe toward expansion, it locked it onto an irreversible path, ensuring that over trillions of years, the night sky will fade to black, leaving only the echoes of a once vibrant cosmos. And yet, in this vast, accelerating emptiness, dark energy remains the same as it ever was: silent, smooth, and utterly unstoppable. Between the glowing threads of the cosmic web lie the universe's most desolate places, vast, empty voids where galaxies are few and far between. Imagine standing in the middle of an empty stadium so large you couldn't see the walls, only to realize it's not just empty, it's growing, stretching, pushing every last speck of matter farther away from you. That's what dark energy is doing on a cosmic scale, accelerating the expansion of these voids until they become some of the emptiest regions in existence. The Boötes void, for example, spans a staggering 330 million light-years, yet contains only a handful of galaxies. If the Milky Way were placed at its center, we wouldn't have discovered the existence of other galaxies until the 1960s. That's how oppressively empty it is. This isn't just random emptiness, it's dark energy's signature. While gravity pulls galaxies together into clusters and filaments, dark energy does the opposite, creating repulsive pressure that pushes matter apart. Over billions of years, it acts like an invisible cosmic landlord, evicting galaxies from these regions one by one. The voids aren't static, they're actively growing, their edges accelerating outward faster than the speed of light relative to distant observers. And because space itself is expanding, the galaxies inside aren't moving, they're being stranded as the void stretches around them, like raisins in an ever-growing loaf of bread. What's truly eerie is that these voids aren't just empty space, they're emptier than empty. Even the sparse gas that lingers in intergalactic space gets diluted further as dark energy stretches the void, leaving behind a near-perfect vacuum. The temperature plummets, and the faint glow of the cosmic microwave background dims as photons lose energy crossing these expanding deserts. If you could float in the heart of one, the night sky would be almost pitch black, with just a few faint smudges of light marking the last surviving galaxies clinging to the edges. Yet these voids aren't just cosmic dead zones, they're also time capsules. Light from galaxies at their edges takes so long to cross the void that we're essentially peering into the past, seeing them as they were when the universe was younger. And because dark energy's effects grow stronger over time, studying voids lets astronomers map its influence across cosmic history. The bigger the void, the more dark energy has sculpted it, making these ghostly regions some of the clearest evidence we have for how the universe's expansion is changing. So while the cosmic web's glittering filaments get all the attention, the voids are where dark energy's power is most brutally evident. They're the universe's shadowy backrooms, places where the rules of gravity are overruled by something far stranger, a force that's not just filling space but defining it, turning emptiness into an ever-growing dominion. And as dark energy's grip tightens, these voids will only grow larger, colder, and more vacant until one day they may be all that's left. One of the biggest mysteries in cosmology today isn't just about dark energy, it's about how fast it's making the universe grow. Scientists call this the Hubble tension, and it's a cosmic detective story where the clues don't add up. Here's the problem: when we measure the universe's expansion rate, known as the Hubble constant, using two different methods, we get two different answers. It's like checking the same speedometer with two tools and getting wildly different readings, except in this case, the speedometer tracks the fate of the entire cosmos. The first method relies on the cosmic microwave background, the afterglow of the Big Bang. By studying subtle temperature fluctuations in this ancient light, scientists can calculate how fast the universe was expanding shortly after its birth, then project that forward to today's rate. The second method skips the early universe entirely, focusing instead on nearby stars and supernova. By measuring their brightness and redshift, how much their light stretches as space expands, we get a direct snapshot of the current expansion. Both approaches are rock solid in principle, but here's the kicker. The cosmic microwave background predicts a slower expansion rate, while local measurements say the universe is flying apart faster. The discrepancy isn't small, it's about 8%, enough to keep cosmologists up at night. So what's going on? One possibility is that dark energy isn't as simple as we thought. Maybe it's not a constant force, but something that evolves over time, growing stronger or weaker in ways we haven't accounted for. Imagine blowing up a balloon where the rubber suddenly starts stretching faster. That's the kind of surprise dark energy might be springing on us. Another tantalizing idea is that our understanding of gravity itself is incomplete. Einstein's theory of general relativity has passed every test for over a century, but what if it breaks down on cosmic scales, subtly altering how the universe expands? Or perhaps there's an unseen ingredient in the cosmic recipe, an extra type of neutrino, exotic dark matter interactions, or even undiscovered dimensions leaking gravity into our universe. Each of these could tweak the expansion rate just enough to explain the mismatch. The Hubble tension isn't just academic nitpicking, it's a potential crack in our model of the universe, one that might reveal entirely new physics. The stakes couldn't be higher. If the discrepancy holds, it could mean rewriting textbooks on how the cosmos works. New telescopes like the James Webb Space Telescope and next-generation cosmic microwave observatories are already hunting for answers, scrutinizing every star and photon for clues. Whatever they find, one thing's certain: the universe isn't playing by the rules we thought we knew, and that's the most exciting kind of mystery there is. The term cold in cold dark matter isn't just a poetic description, it's a cosmic speed limit that shaped the entire universe. Unlike particles zipping around at near light speed, cold dark matter moves sluggishly, more like a slow-moving crowd than a swarm of frenzied bees. This lethargic pace was crucial in the early cosmos because only slow-moving particles could clump together under gravity's pull, forming the seeds of galaxies. Picture trying to build a sandcastle with dry, loose sand. The grains slip through your fingers before anything sticks. Now imagine wet sand, heavy and cohesive, molding easily into towers and walls. Cold dark matter was the wet sand of the cosmos, dense enough to collapse into vast structures while ordinary matter, hot and chaotic, lagged behind. This slowness wasn't just convenient, it was necessary. If dark matter had been hot, meaning its particles moved at relativistic speeds, they would have streamed freely across the infant universe, smearing out density fluctuations before galaxies could form. The cosmic web would look more like a faint mist than the intricate lattice we observe today. But because cold dark matter particles lumbered along, gravity had time to corral them into deep wells, dragging ordinary matter along for the ride. Simulations show this perfectly when scientists tweak the model to use faster-moving, warm, dark matter instead. Large galaxy clusters fail to appear on time, leaving the universe looking threadbare and underdeveloped. What's fascinating is how this coldness leaves fingerprints across cosmic history. The pattern of galaxy clustering, the timing of the first stars, even the faint ripples in the cosmic microwave background all point to dark matter being slow-moving from the very beginning. And unlike ordinary matter, which heats up and radiates energy when compressed, cold dark matter stays cool, piling up without friction or resistance. It's why galaxies can nest inside sprawling halos hundreds of times larger than their visible disks. The dark matter just keeps accumulating, silent and undisturbed. Yet, even with all this evidence, the cold in cold dark matter isn't absolute. Some theories suggest a small fraction might be slightly warmer, with particles moving at a few % of light speed. This could explain oddities like certain dwarf galaxies having fewer satellites than expected, or the inner regions of galaxies being less dense than models predict. It's a reminder that dark matter's story might have nuance, a dominant chorus of slow-moving particles with a faint, faster undertone weaving through them. One thing's certain: without cold dark matter's patient, gravitational embrace, the universe would be a far emptier place. The majestic spirals of galaxies, the glowing clusters, even the voids between them, all owe their existence to particles moving just slowly enough to let structure take hold. It's a delicate balance, one that turned a formless early universe into the rich tapestry we see today, all because dark matter knew when to take its time. Phantom energy isn't just dark energy's stronger cousin, it's a cosmic doomsday scenario with a timer attached. While ordinary dark energy accelerates the universe's expansion at a steady pace, phantom energy dials that up to catastrophic levels, growing stronger over time until reality itself starts unraveling. Picture a rubber band stretching gently at first, then faster and faster until with a final snap it shreds into pieces. That's phantom energies in-game, a big rip where galaxies, stars, and even atoms are torn apart by the unrelenting expansion of spacetime. This isn't just theoretical doom-mongering, the math checks out. Phantom energy would require the equation of state, a measure of how its pressure relates to its density, to dip below -1, creating a repulsive force that doesn't just push space apart but amplifies as it stretches. It's like a car's accelerator pedal getting stuck while going downhill. The speed doesn't just increase, it spirals out of control. Over billions of years, this runaway effect would escalate until the very fabric of spacetime can't take the strain. The timeline is as chilling as the concept. First, galaxy clusters would be ripped apart, their gravitational bonds overpowered by the stretching vacuum between them. Next, individual galaxies would disintegrate, stars flung into the void like sparks from a firework. In the final moments, phantom energy would overcome the forces holding planets, molecules, and even atomic nuclei together. Protons and electrons, once inseparable, would be wrenched apart in a final, violent instant. The universe wouldn't just fade into cold isolation, it would be dissected piece by piece down to the quantum level. What makes phantom energy especially eerie is how little it would take to tip the scales. Current observations place dark energy's equation of state tantalizingly close to -1, with a margin of error that just includes the phantom zone. We might already be on that path, with the universe's fate hinging on measurements we can't yet make with certainty. Future telescopes, like the European Space Agency's Euclid mission, aim to nail down this number with unprecedented precision, either ruling out phantom energy or forcing us to confront an expiration date for existence itself. The Big Rip isn't the only possible in-game, but it's the most visceral. Unlike the slow fade of the Big Freeze or the fiery collapse of the Big Crunch, it's a finale written in sudden, violent crescendo. And while the odds might be slim, the mere possibility reminds us how fragile our cosmic scaffolding really is, balanced on equations we're only beginning to decode. Phantom energy isn't just a hypothetical, it's a dare to the universe, challenging us to prove it wrong before the clock runs out. If dark matter truly forms invisible halos around galaxies, then where are all the tiny galaxies it should have spawned? This is the missing satellite problem, one of the most persistent headaches in modern astrophysics. Computer simulations of cosmic evolution, based on our best understanding of dark matter, predict hundreds of small satellite galaxies orbiting Milky Way-sized systems. Yet when astronomers count them, they find only a few dozen at most. It's like expecting a bustling crowd around a concert venue, but arriving to find just a handful of stragglers. Something's clearly off. The discrepancy isn't trivial. According to cold dark matter theory, the early universe should have been peppered with tiny density fluctuations, each growing into clumps of dark matter. These clumps, some no heavier than 1,000,000 suns, would act as gravitational traps, pulling in gas to form small, faint galaxies. Yet when we survey our cosmic neighborhood, these dwarfs are conspicuously absent. The Milky Way, for example, has about 60 known satellite galaxies, far fewer than the hundreds or even thousands most simulations suggest. Even more puzzling, the ones we do see are oddly clustered together, not scattered evenly as predicted. So what's hiding the missing satellites? One leading idea is that our simulations overestimate how many would survive to the present day. Perhaps many of these small dark matter clumps did form but never captured enough gas to ignite stars, leaving them invisible to our telescopes. Another possibility is that early bursts of radiation from the first stars, a phenomenon called reionization, stripped gas away from these fledgling galaxies before they could properly form, leaving them dark and undetectable. Imagine a gust of wind blowing out candles. As soon as they're lit, only a few, sheltered from the blast, manage to stay glowing. But there's a twist. Some astronomers argue the problem isn't with dark matter, but with how we're looking. Recent ultra-sensitive surveys, like the Dark Energy Survey and the Gaia spacecraft, have uncovered streams of stars and ultra-faint dwarfs so dim they were previously overlooked. These discoveries hint that the missing satellites might be lurking in plain sight, just too faint to see without cutting-edge tools. It's like realizing the concert crowd isn't missing. They're just all wearing black, camouflaged against the night sky. Yet, even with these discoveries, the numbers still don't quite match. That's led to more radical proposals, like the idea that dark matter might interact with itself or with ordinary matter in ways we haven't accounted for. If dark matter particles exerted even a tiny amount of pressure or friction, it could smooth out small-scale clumps, preventing them from growing into visible galaxies. Alternatively, maybe dark matter isn't entirely cold. Perhaps a fraction of it moves fast enough to escape the smallest halos, thinning out their numbers. Whatever the answer, the missing satellite problem isn't just about counting dwarfs. It's a stress test for our entire understanding of cosmic structure. Solve it, and we might unlock secrets about dark matter's true nature. Fail to solve it, and we could be forced to rewrite the rules of galaxy formation altogether. The universe, it seems, loves leaving us just enough clues to keep us guessing, but never quite enough to spill all its secrets at once. Neutrinos are the universe's ultimate ghosts, particles so elusive they can pass through a light year of solid lead without a single collision. Born in the nuclear furnaces of stars and the violent deaths of supernova, trillions of them stream through your body every second, leaving no trace. For decades, scientists assumed these particles were completely massless, zipping through the cosmos at nearly the speed of light. But in the late 1990s, something extraordinary happened. Experiments revealed that neutrinos do have mass, albeit vanishingly small, so tiny that even the lightest known particle, the electron, outweighs them by a factor of at least 1 million. This discovery cracked open a fascinating possibility. Could these relic neutrinos, left over from the Big Bang, account for some of the universe's missing dark matter? After all, they're everywhere, filling space with an invisible sea of nearly undetectable particles. The math, however, tells a different story. Even with their colossal numbers, neutrinos are simply too light to explain more than a fraction of dark matter's gravitational pull. At best, they might contribute around 1% of the total dark matter density, a drop in the cosmic bucket. Why so little? It all comes down to speed. Neutrinos from the early universe moved so fast close to light speed that they couldn't clump together under gravity's pull like cold dark matter does. Instead, they zipped freely across space, smoothing out the density fluctuations that would later seed galaxies. Picture trying to gather a swarm of hyperactive fireflies into a tight ball. They just scatter in every direction. That's why scientists call this hypothetical neutrino-dominated scenario hot dark matter, a model that, when simulated, produces a universe far more formless and diffuse than the structured cosmos we observe. But here's where it gets even more interesting. While relic neutrinos can't be the primary dark matter candidate, their minuscule mass still leaves fingerprints on cosmic evolution. Their high-speed motion dampened the growth of the smallest primordial structures, subtly altering the distribution of galaxies we see today. Ultra-sensitive telescopes have even detected this effect, a faint suppression of clustering on the smallest scales, like a cosmic whisper of neutrinos' fleeting gravitational influence. The takeaway: neutrinos are a reminder that dark matter isn't a single puzzle but a mosaic of mysteries. They might not solve the bulk of the problem, but their existence hints at a universe richer and more nuanced than we ever imagined. One where even the tiniest particles can shape the grandest cosmic structures in ways we're only beginning to decode. The KBC void isn't just another cosmic oddity. It's a colossal bubble of nothingness that might rewrite our understanding of the universe's expansion. Named after astronomers Keenan, Barger, and Cowie, who identified it in 2013, this spherical region stretches over 2 billion light-years across, making it one of the largest known structures in existence. But here's the twist: it's not empty. It's just emptier than it should be, with roughly 20% fewer galaxies than the cosmic average. If you were floating at its center, the night sky would appear eerily sparse, like standing in a half-abandoned city where most of the streetlights have gone dark. What makes the KBC void so controversial is its location. We're inside it. That's right, the Milky Way sits slightly off-center in this vast underdense region, which raises a startling question. Could our local cosmic address be skewing our measurements of the universe's expansion? Dark energy's discovery hinges on the observed acceleration of distant galaxies, but if we're sitting in a giant void, gravity's pull would be weaker here, making it look like space is stretching faster than it really is. It's like trying to measure ocean currents while bobbing in a whirlpool. Your local environment distorts the bigger picture. This Hubble bubble hypothesis challenges the standard model of cosmology, where the universe is assumed to be roughly uniform on large scales. If the KBC void is real and as extreme as some data suggests, it could mean dark energy's influence has been overestimated, or that we need to rethink how structures form in the first place. Some theorists argue such a void shouldn't exist in current simulations of cold dark matter, which predict a more even distribution of matter. Others counter that while rare, these underdense regions aren't impossible, just incredibly unlikely, like finding a single grain of sand in a desert that's slightly smoother than the rest. The debate isn't just academic. If the void's gravity is indeed tugging galaxies outward, it could explain why different methods of measuring the universe's expansion rate, like the Hubble tension, don't agree. But proving it's real is another matter. Mapping the KBC void requires painstaking surveys of galaxy densities across billions of light-years, a task complicated by the fact we're embedded within it, like trying to map a forest from inside a foggy clearing. New telescopes like the Vera Rubin Observatory aim to settle the controversy by charting galaxy distributions with unprecedented precision. Whether the KBC void is a cosmic fluke or a fundamental challenge to dark energy's dominance, one thing's certain: it reminds us that the universe is full of surprises. Even as we peer deeper into space, our own backyard might still hold secrets that reshape everything we thought we knew. And if this void is real, it's not just a curiosity, it's a wake-up call that the cosmos is far more complex and far more mysterious than our models have dared to predict. Long before galaxies and stars flickered into existence, the universe hummed with a faint but persistent tremor, quantum fluctuations so small they'd vanish in a heartbeat, yet powerful enough to shape everything we see today. Picture the surface of a still pond suddenly disturbed by a gust of wind, creating ripples that grow and spread. In the first trillionth of a second after the Big Bang, space-time itself trembled with these microscopic irregularities, tiny variations in density that would become the blueprint for the entire cosmic web. And here's the astonishing part: dark matter, the invisible scaffolding of the universe, was the first to respond to these quantum whispers, amplifying them into the vast structure we observe now. How did something so small seed something so colossal? It all comes down to gravity's relentless patience. Those initial quantum ripples created slightly denser regions where dark matter, cold and slow-moving, began to clump together. Over billions of years, these faint overdensities grew like cosmic snowballs, gathering more dark matter until their gravitational pull became strong enough to drag ordinary matter, gas, dust, and eventually stars into their embrace. The result, a sprawling network of filaments and voids with galaxies clustering like dew on a spider's silk. Those quantum tremors didn't just fade into oblivion. They echoed across eternity, sculpting the universe on the grandest scales. What's even wilder is that we can still see these primordial fingerprints today, etched into the cosmic microwave background, the afterglow of the Big Bang. Satellite missions like Planck have mapped its subtle temperature variations, revealing a pattern almost identical to the distribution of galaxies we observe now. It's as if the universe left us a recipe: start with quantum foam, add dark matter, let gravity simmer for 13 billion years, and voila, a cosmos teeming with structure. But the story doesn't end there. Some theories suggest dark matter might not have been a passive player in this process. Certain models propose that dark matter particles could have interacted with each other in the early universe, creating additional ripples or even delaying the formation of the first stars. Others speculate that quantum fluctuations didn't just seed dark matter's distribution, they might have birthed primordial black holes now lurking in the hearts of galaxies. One thing's certain: without those fleeting quantum shivers in the infancy of space-time, the universe would be a flat, featureless void. No spiraling galaxies, no glittering superclusters, no cosmic web, just an endless, sterile expanse. So the next time you gaze at the night sky, remember, you're seeing the aftermath of a quantum whisper, a ripple that refused to fade, written in dark matter's invisible ink. Deep within the cosmic microwave background, the faded glow of the Big Bang, there's something that shouldn't exist. Scientists call it the axis of evil, a name that sounds like it's straight out of a sci-fi thriller, but the reality is even stranger. This mysterious pattern in the CMB reveals an eerie alignment of hot and cold spots that defies conventional cosmology, suggesting dark energy might not be as uniform as we thought. Imagine throwing confetti into the air, and instead of scattering randomly, it arranged itself into a perfect arrow pointing in one direction. That's the level of cosmic unease the axis of evil has stirred among physicists. At the heart of the mystery is the CMB's near-perfect uniformity, a relic of the early universe's extreme heat and density. Tiny fluctuations in this ancient light should be random, like static on an old TV, with no preferred direction or alignment. But when researchers mapped these fluctuations, they found an unsettling pattern. The hot and cold spots appear to line up along a particular axis, as if the universe has a hidden, preferred direction that contradicts the bedrock principle of cosmological isotropy, the idea that the universe should look the same in all directions. It's as if you spun a globe blindfolded, and every time your finger landed on the same latitude. What does this have to do with dark energy? If the universe's expansion is being driven by a perfectly uniform force, as the standard model assumes, there's no reason for cosmic structures to align along a specific axis. Yet the axis of evil suggests that dark energy, or something even more exotic, might be distributed unevenly, creating subtle ripples in space-time that nudge the CMB into this bizarre configuration. Some theories propose that dark energy could clump like dark matter, forming vast domains where its strength varies. Others speculate that our universe might be part of a larger multiverse, with neighboring universes exerting gravitational tugs that warp our CMB like fingerprints on a balloon. The implications are profound. If the axis of evil is real, and not just a statistical fluke or measurement error, it could mean our understanding of dark energy is incomplete, or that entirely new physics is at play. Even the name reflects how unsettling this anomaly is. Scientists don't dub things evil lightly. Some have tried to dismiss it as a coincidence, but multiple independent studies have confirmed the signal, including data from the Planck satellite, one of the most precise CMB maps ever made. The odds of such an alignment happening by chance, less than 1 in 1,000. So why haven't we heard more about it? Because the axis of evil lies in the uncomfortable gap between discovery and explanation. It's too persistent to ignore, but too perplexing to fit neatly into existing theories. Like a ghost in the cosmic machine, it haunts the edges of our models, whispering that the universe might be stranger and far less random than we ever imagined. Whether it's a clue to dark energy's secrets or a sign of something deeper, one thing's certain: the cosmos has a way of humbling us, revealing its mysteries only when we're ready to question what we think we know. Galaxies don't float alone in space. They're cocooned inside vast, invisible spheres of dark matter, like fireflies trapped in amber. These halos, stretching far beyond the luminous edges of galaxies, are the universe's hidden scaffolding, holding stars together against the relentless pull of cosmic expansion. Picture a merry-go-round spinning at breakneck speed without something anchoring the riders. They'd fly off into the void. That's exactly what would happen to galaxies without their dark matter halos, their stars flung into the abyss by centrifugal force. Yet somehow, galaxies spin faster than their visible mass should allow, a discrepancy astronomers first noticed in the 1930s when Fritz Zwicky observed galaxies in the Coma cluster moving as if gripped by an unseen hand. The numbers are staggering. A typical halo contains up to 10 times more mass than all the stars, gas, and dust in the galaxy it envelops. Our own Milky Way is no exception. Its halo stretches nearly 1 million light-years across, a ghostly sphere so large it could swallow the Andromeda galaxy whole with room to spare. But here's the catch: these halos aren't solid or even dense. Dark matter particles are so thinly spread that you could pass through a halo and never notice, though trillions of them stream through your body every second. Their power lies not in density but in sheer volume, their collective gravity bending space-time like a cosmic fingerprint. This halo effect solves one of astronomy's oldest puzzles, the missing mass problem. For decades, the motion of stars and gas in galaxies defied Newton's laws, as if the visible matter was just the tip of a much larger iceberg. The math never added up until dark matter's gravitational signature filled the gap. Even more mind-bending, halos aren't static. They grow over time, merging and colliding as galaxies interact. When the Milky Way and Andromeda eventually collide, their halos will entwine first, a silent dance of invisible giants that sets the stage for the starry spectacle to follow. Yet halos aren't perfect spheres. They're lumpy, asymmetrical, and riddled with substructure. Simulations reveal smaller clumps of dark matter orbiting within them like moons around a planet. Some of these clumps may host failed galaxies, pockets of gas that never ignited into stars, while others could be pure dark matter, invisible even to our most sensitive telescopes. Their presence explains why galaxies don't spin like rigid disks but more like swirls of cream in coffee, their outer stars lagging behind the inner ones, a phenomenon that baffled astronomers before dark matter entered the picture. But the real magic of halos lies in their universality. From the tiniest dwarf galaxies to the largest superclusters, dark matter's gravitational embrace follows the same blueprint, a cosmic rulebook written in unseen ink. Without these halos, the night sky would be unrecognizable. No spiral arms, no galactic clusters, just isolated stars adrift in an endless void. So when you look at a galaxy, remember, what you're seeing is just the glittering jewelry. The real treasure, the force that binds it all together, remains hidden, a silent guardian shaping the universe from the shadows. The night sky of the far future will be a lonely place, not because the stars have vanished, but because dark energy will have rewritten the rules of what's visible. Imagine an astronomer 10 trillion years from now, peering through a telescope only to find the cosmos has gone dark beyond their local cluster. Every galaxy outside their immediate neighborhood will have been dragged beyond the cosmic horizon by dark energy's relentless push, their light stretched into undetectable infrared whispers. What we see today as a glittering tapestry of galaxies will fade like footprints in a rising tide, erased by the expansion of space itself. This eerie future stems from dark energy's most unsettling property. Its density doesn't dilute as the universe grows. While matter thins out, dark energy maintains constant pressure, like an infinite spring woven into the fabric of space-time. As distances between galaxies increase, dark energies influence snowballs, accelerating expansion until distant objects recede faster than light can bridge the gap. The consequences unfold in stages. First, galaxies outside our local group will redshift into invisibility within 100 billion years. Next, the cosmic microwave background, the afterglow of the Big Bang, will dim beyond detection as its wavelengths stretch into meaningless radio noise. Eventually, even the elemental evidence of expansion, the redshifted light of fleeing galaxies, will vanish, leaving future civilizations with no clue the universe is expanding at all. What makes this isolation so profound is how it rewrites cosmic history. Without visible evidence of receding galaxies or remnant radiation, astronomers in this distant era might conclude the universe is static and finite, a lone island of stars in an eternal void. All traces of the Big Bang, dark energy, even the existence of other galactic clusters, will be lost to the stretching expanse. It's as if the cosmos is systematically burning its own history books, leaving future generations with only the final chapter. Yet this grim fate holds a bizarre silver lining. Collisions between Milky Way and Andromeda will create a spectacular new galaxy Milkdromeda, while the remnants of our local group continue orbiting each other in gravitational harmony. For civilizations within this bound cluster, life could continue for eternity, unaware of the desolation beyond. Stars will still form from recycled gas, planets will orbit, and the night sky, though diminished, will never go completely dark. The ultimate irony, dark energy's greatest triumph, erasing all evidence of itself, might be its own undoing. Without observable expansion, future scientists could mistake their lonely galactic cluster for the entire universe, reconstructing cosmology from scratch with no hint of the dark forces that shaped reality. The very phenomenon that dominates the cosmos today will become its most thoroughly hidden secret, leaving only one question: how many times has this cycle already happened in the endless expanse of eternity? What if our universe's dark energy isn't a cosmic constant, but just one random setting in a vast multiverse of possibilities? This isn't science fiction. It's a cutting-edge theory that could explain why dark energy's value seems bizarrely fine-tuned for life. In countless other universes, dark energy might be so weak that gravity crushes everything into black holes before stars form, or so strong that matter is ripped apart before atoms can even bond. Our universe's Goldilocks perfect balance, where dark energy is just strong enough to accelerate expansion without obliterating structure, could be sheer luck, a single winning ticket in a cosmic lottery with infinite losers. The multiverse idea stems from string theory and inflationary cosmology, where pocket universes bubble up endlessly, each with different physical constants. Dark energy's value in this scenario isn't special, it's random, like the spin of a roulette wheel landing on our number by chance. Some universes might have dark energy 1 billion times stronger, exploding into empty voids instantly. Others could have none, collapsing back into singularities moments after birth. The wildest part, if these universes exist, we'd never see them. They're disconnected from ours, hidden beyond the reach of space and time. But here's where it gets even stranger. Dark energy's odd value, just enough to dominate the cosmos now, after billions of years of structure formation, might be a clue that we're in a typical universe where life can arise. If most habitable universes require dark energy values like ours, our observation of its strength isn't a puzzle, it's a selection effect. We're here because this universe allowed galaxies, stars, and eventually us to exist. This anthropic principle turns the mystery on its head. Dark energy isn't fine-tuned for life. Life emerges where dark energy isn't lethal. Some theorists take this further, suggesting dark energy could be a bridge between universes, a leakage of energy from neighboring dimensions warping our spacetime. Imagine bubbles in a boiling pot, each pressing against the others, subtly influencing their expansion. If true, dark energy's repulsive force might not even be ours, but an echo of other realities brushing against our own. Of course, the multiverse remains untestable for now, lurking in the realm of mathematical speculation. But if future experiments find patterns in the cosmic microwave background suggesting collisions with other universes, or if string theory narrows down possible dark energy values, this wild idea could vault into mainstream science. Until then, dark energy's connection to the multiverse remains one of cosmology's most tantalizing what-ifs, a reminder that the weirdness we see might just be the tip of an infinite, invisible iceberg. From ghostly halos binding galaxies to the universe's accelerating fate, dark matter and dark energy aren't just footnotes in cosmology, they're the invisible architects of reality itself. We've journeyed through 25 mind-bending truths: how dark matter's gravitational scaffolding shaped the cosmic web, how dark energy's repulsive force could one day tear atoms apart, and how these mysteries humbly remind us that 95% of the universe remains hidden in plain sight. Think about that: everything we've ever observed, from the tiniest microbe to the grandest supercluster, is just the shimmering surface of a fathomless dark ocean. These discoveries rewrite cosmic history. Without dark matter, galaxies would never have formed. Without dark energy, the universe might have collapsed long ago. We've seen how Einstein's blunder became the key to dark energy, how Vera Rubin's stubborn starlight revealed dark matter's grip, and how quantum whispers in the infant universe grew into the vast structures we see today. Even now, experiments hunt for WIMP and axions, while telescopes probe voids and the axis of evil, each clue peeling back another layer of this enigma. But here's the thrilling part: we're still at the beginning. Every unanswered question why dark energy's density stays constant, what dark matter truly is, whether phantom energy lurks in the equations, is a doorway to deeper understanding. Future breakthroughs could unveil entirely new physics, extra dimensions, or even a multiverse of cosmic possibilities. The universe has a way of surprising us, turning yesterday's impossibilities into today's textbooks. So as you look up at the night sky, remember, the stars are just the prologue. The real story is written in the dark, waiting for the next curious mind to decode it. What do you think lies beyond our current understanding? Could dark matter particles be hiding in plain sight, or is the truth stranger than we've dared to imagine? Drop your wildest theories in the comments, and if you're hungry for more cosmic mysteries, hit subscribe. The universe isn't done revealing its secrets, and neither are we. Until next time, keep looking up and wondering what's out there in the dark.